Good morning, everyone. My name is Tin Vuong. I'm a senior undergraduate computer science student at Ohio University. I'm joined today by Dr. Cheng Liu, who is my mentor and one of the co-authors of this presentations. And the main presenter was supposed to be a graduate student, Krikit, right here, but since he couldn't make it today, I will be the stand-in presenter. And also with help of Alex Bukowski as well, who is not here today. So, a little bit about what the project is about. So basically, we are trying to explore LLM's capability in positional reasoning, and we thought that Wordle is like the perfect game to do this. And has anyone here not played Wordle before? Okay, so I'll just go do a very quick demo of what Wordle is like. So if you go to Wordle, so it's basically a word guessing game. So I'll type in a random word, and then gray indicates that that letter is not in the correct word. A yellow indicates that that character is present in the word, but in the wrong position. And green it stands for correct character and also position. And so you're given 6 attempts in Wordle, and you have to deduce a 5-letter word. But we also explore another Wordle variant, which is called Fibble. So there's gonna be 1 to 5 lies depending on the level you're playing. So introduce per row in the Wordle guess, in the Fibble guess. So that's why you're given more attempts, 9 attempts. And so this was more like kind of like a classroom discussion project. So we were able to get a lot of submissions from students. So I have 16 here, and so like I mentioned before, we wanted to explore the LLM's capability in positional reasoning, and this is because our hypothesis is that LLM would struggle with word games because of the tokenization problems. So for example, for the word stank, LLMs don't actually see like every single character of that word, or let's see the whole word itself. It's tokenized into 2 different, group of words there. So ST and an ANK, right? And so if you ask it, is the character N in position 4? It doesn't really know, right? Because before these groups of characters are fed into the neural network, transformers, whatever, they just becomes numbers, right? And so A and K will be represented by a single number. So there's not really information about whether the character N is in position 4 of the word stank or not. And so our hypothesis is that with Wordle, it will struggle a little bit. But with Fibble, however, when you introduce the lies to the character, so like say, if you say if it shows A is in the correct position, but is actually not, then it increases the search space of the problem, right? And so our hypothesis is that the performance will degrade when deceptive feedback is introduced, and the more lies you introduce, the worse the model is going to perform. Okay, and our evaluation metrics for this problems includes win rates, average guesses per game, invalid guess ratio. So it's trying to guess like A, B, C, D, E, for example. That's not a valid word. And there shouldn't be we didn't really measure prompt size at the end because we tried to keep it as uniform as possible across multiple models, right? So for the Wordle results here, we tested it with both commercials and local models from Olama. And he has a few participants, so myself included. I tested this model like yesterday, 100 games of Wordle, local model GOM, 30 billion parameters, and it solved it 100% of the times with an average of 4 tries. And other models, Olama, also had the same performance. And for commercial models, GPT-5, the most recent models, solved it 100% of the times. But if you look at the open source model they released last year, the 20 billion models, and also GPT 4.0, they actually didn't perform as well. And so there are parameter size, model size, and also when the model was released. Those two factors also come in play as well. And the really small models, so 4 billion parameters and smaller, that basically barely even solve the game. And so there was one really impressive result from one of the students. So using a model with only 8 billion parameters, he was able to solve Wordle 100% of the time, so an average of only 3.7 tries. That is even better than 5.9 from GPT-5. And so the main improvement, I guess, the main techniques that he did was constraint filtering. So meaning like, say, if there's only one possible word in the next guess, so say you have discovered 4 letters, there's only 1 letter left, there's no other valid English word that you could guess beside the correct one, then you don't have to call LLM, right? Like that. And also making sure that the LLM doesn't guess. Let's say if a character is in the correct position and it gives you another character in that position, then you would kind of like pre-prompt it, tell it like think again because this character is in the correct position, those kinds of things. And for Fibble, the results are quite different. We didn't include average tries here because I think I wasn't really the main presenter of this presentation, and it wasn't included, so my apologies. Fibble 1 was solved by most of the commercial models 100% of the time. But as you can see, when we move on to higher levels, introducing more lines, increasing the search space exponentially, the performance degrades. And interestingly, GPT-5 was able to solve Fibble 5 90% of the time. But other smaller models weren't able to solve them. And for local models, the smaller models, they basically struggle and couldn't even solve it most of the time. And here just more the top performers of the submissions. And yeah. And so one impressive result is in Fibble was from GPT-5 with low reasoning. And as expected, when more lines are introduced, the performance degraded. But interestingly, when introduced with 5 lines, the model was able to solve it better than 3 or 4 lines. And honestly, I couldn't tell you why.
Well, the reason why is because when all feedbacks are live, you can now don't have to guess which one is live. You know all of them are live. So that actually gives you information. We didn't know in the very beginning. It's only when the result came out, it was like, oh, that, yeah.
Yeah, that was nice. So just to summarize the results, all commercial APIs were successfully solving Wordle 100% of the time. Mid-tier models, so models greater than with more than 8 billion parameters, solved it like most of the time. but smaller models achieve pretty much didn't solve them. But one note is that if you prompt the model cleverly enough, so like telling it that, well, if it tries to guess a character which is what is in the wrong position, then you would reprompt it. Those kinds of things, and also telling it to start with some like really common words that includes a lot of vowels, for example. That would improve its performance. And like I said before, constraint filtering with a smaller model achieve an even better efficiency than just like raw prompting a commercial model. And for Fibble, on the other hand, even the current flagship commercial models fail at the higher level of Fibble, and we believe that this is because of the exponential search space that increases as you make more guesses, and also as more lies are introduced to the game as well. And yeah, even prompt engineering, like trying to make the prompt better, didn't really improve the model's performance. And with this, I would like to show something that's I think is quite interesting by one of the GPT models. So this is one of the logs that we have of Fibble 2 played by a GPT open source model, 20 billion parameters. So 2 lies, 9 tries. Oh.
Thank you.
Yes. How's that for people in the back? All right. Okay, so 2 lies, 9 tries, GPT 20 billion parameters, Olama. It did a bunch of reasoning. They did the results in the middle of the game, but then something that I never expected happen did happen. So the reasoning through the word, whatever, blah blah blah, and then bottom line, guessing on row 6. Oh, and then it started speaking Japanese, calculating position, velocity for some reason. And I was like, I didn't know Wordle or Fibble was this serious, you know? Yeah. But like, I guess this was last year, so before they released the guardrail model, the open source guardrail model. So we haven't tried that yet, but that's something that I would love to find out if they fixed this problem or not. I couldn't tell you. But yeah, just something. So our conclusion is therefore what games do indeed expose LLMs weaknesses in the character level position reasoning, especially for smaller models. Like I don't know if you guys remember this one meme that was really famous like last year, where GPT can count how many R's are in strawberries, you know. So that was kind of like one of the motivations as well. But like I said, Fibble, where there are lies introduced, introduces an exponential hypothesis space, so that makes it even harder, right? And using prompt engineering with some constraint filtering, that often outperforms a commercial pure just raw prompting LLM. And so it validated our hypothesis, and the evidence for the DeepSeek's claim that LLMs cannot reliably or consistently understand character level reasoning. And future directions. So I don't know if you've seen from the results page. I'll just go back for a little bit. Since I'll just use this one. Since this was like a class activities, not a lot of students had access to computational resources, GPUs, so they couldn't run as many games as the number of games ran was uneven across students. So what we would like to do is to run 100 games for each of the models, just to be more statistically accurate. And also standardizing the LLMs output, just because different APIs give different formats, and also local models usually struggle with this problem as well. And we do have a real-time leaderboard. I think it should be in one of the links here. Yes. So we do have real-time leaderboards. So in this link right here, drchangliu.github.io/Wordle Arena. If you go to that link, you can see our current live leaderboard of that is being updated every day, asking LLMs to play Wordle. Yep. And also, we would like to try it with other game variants as well. So one of the games is called Clueless. Has anyone here played Clueless? Basically, you guess a word, and it gives you a score to indicating how close you are to the hidden word. And so, if say, for example, the correct word is like piano, and then first you guess movie, that's probably not close. But if you guess music, then it will indicate a higher score. And so you try to get as close as you can to the hidden word. And we didn't really include latency in this in the metrics, because personally I think that shouldn't really be a problem. That doesn't really, I guess, match our what we're trying to test, our hypothesis, right? So. So future directions, including just forcing chain of thought actually improve models' performance, because right now we're just like kind of like prompting the LLM doesn't really tell it to like kind of like go back, think about what you guessed, and then see if it makes sense, right? And also trying it with reasoning models as well. And also, can external memory tracking improve the Fibble performance? Because as mentioned before, the exponential search space makes the LLM it kind of like increases the context window of it, and it start hallucinating as well. And just combining multiple models, much larger models. Yeah, and more. There's just more of what was said, and I think that's it. Thank you. Do we have time for questions?
We have questions as the panel at the end.
Okay.
My name is Pradhan. I'm a master's student in computer science at NYU, and I'm also researching in Games and Innovation Lab. And I'm going to talk about how we use wave function collapse to generate playable puzzles in Pokemon Fire Red. This work sits at the intersection of procedural content generation and puzzle design for top-down RPGs. Our goal wasn't just to generate maps that look valid, but maps that are actually solvable, interesting, and fun to play. So, to ground this work, we start with Pokemon Fire Red, specifically the Viridian Forest Maze. It's one of the few puzzle-like environments in the game, and that provides a clear baseline for what works and what doesn't. So when you look at the original Forest Maze, there are a few big limitations. It's not very replayable. There's very little interesting structure once you know the solution, and the game only really has one type of forest-style puzzle map, which are always mazes. That makes it an ideal candidate for procedural content generation. To address this, we turn to procedural content generation, specifically wave function collapse. WFC is a constraint satisfaction method that generates new content by learning local adjacency patterns from a single example. You observe tiles, initialize an unknown grid, and iteratively collapse tiles while respecting the constraints. To apply WFC to fire rate, we first pass the raw maps into a tile-based representation. Each tile is assigned an ID, and we learn adjacency rules and frequency weights from the original map. This gives us a traditional rule-based WFC setup. However, the naive WFC has serious problems. The generated maps often aren't challenging, and worse, they're frequently unsolvable. This is a core issue. Visual plausibility doesn't guarantee playability. As you can see, the red box over there is the goal tile, the goal/destination tile, but we can't actually get to it while walking. So this leads directly to a research question: can we use WFC to procedurally generate top-down RPG puzzles that are structurally coherent, complex, and playable? Everything that follows is about answering that question. To explore this space, we didn't design multiple fundamentally different models. Instead, we designed a single WFC-based generation model and explored two different approaches to using it. Each approach progressively adds more structure and gameplay-aware constraints on top of standard WFC. So the core algorithm stays the same, but the way we guide and constrain generation changes how playable and complex the resulting maps are. So we apply WFC to forest map generation using a two-phase approach. In the first phase, we generate a simple high-level structure by explicitly defining entry and exit points and carving a random solution path between them. This guarantees that a valid path this guarantees that there is a valid path through the map. In the second phase, we run the WFC, but with constraints tied to this structure. We define a specific tile set for the solution path, and during collapse, any cell marked as part of the path is only allowed to collapse into the tiles from that set only. This lets WFC fill in the surrounding forest naturally while preserving guaranteed playable path. To increase puzzle complexity, we integrate Sokoban-style rock puzzles into our forest maps. In Sokoban, the player pushes boxes into designated storage locations within a grid-based environment, which makes it a good test case for a structured, constraint-heavy puzzle. We use WFC to generate Sokoban layouts by learning valid local patterns from example puzzles. These layouts are generated independently, verified for correctness, and then embedded into specific regions of the forest map as additional constraint during WFC generation. So in our first approach, which we call optional rock puzzles, we start by generating a guaranteed solution path through the map. Once that path exists, we search for rectangular regions along the map that are suitable for embedding Sokoban puzzles. These regions are passed into a Sokoban generator where all tiles are required to be walkable and valid for pushing mechanics. The generated Sokoban layouts are then overlaid back onto the map as additional constraints. Finally, we assign all marked phase 1 blocks such as solution path tiles, boxes, holes, Sokoban walls and floors, the map, the players and blockers into the respective tile sets, and run a final WFC pass to seamlessly integrate everything into a single playable map. To encourage interaction, we introduce a scoring system. Players lose points per move. Entering a puzzle has a small penalty, but solving a puzzle gives a large reward. Importantly, the game can still be completed without solving any puzzles. In our second approach, required rock puzzles, Sokoban puzzles are no longer optional. Instead, they gate player progression. We introduce a candy collection mechanic where the player must solve specific Sokoban puzzles in order to collect candies and unlock the path forward. Once the required candy is collected, the stones in that region can still be freely pushed, which prevents soft locks and keep the environment flexible after the puzzle is solved. To evaluate these models, we focus on 3 properties: solvability, total player moves, and whether alternative paths exist. We use two-layer connected A-star agent. One layer solves the maze navigation problem and the other solves Sokoban puzzles when encountered. A-star is a standard pathfinding algorithm that balances the path cost and heuristic distance. It's well suited for evaluating solvability and complexity in grid-based games. For the maze, movement costs 1 and entering a puzzle costs half. For Sokoban, movement costs 1, pushes are free, and the heuristic is the sum distance of rocks to the goals. Here you can see the solver in action. The purple path represents the A-star solver's computed solution path through the generated maze. This is the optimal path found by the search algorithm. On the right, we display solver statistics for the Sokoban region. We report the number of solving steps, node expansion, and solving time. Below that, we show the same metrics for full generated map, including the outer maze and embedded puzzle regions. This visualization confirms two things. First, that the map is solvable end-to-end, and second, the solver remains computationally efficient even as structural complexity increases. On the left, the yellow path is the initial carved solution path before WFC, which guarantees solvability. After WFC expands the structure, the purple path on the right shows the A-star solver's optimal route. The fact that it differs from the original path shows that alternative routes naturally emerge, making the maze more exploratory and replayable. Here we compare our A-star solver with 20 human testers to understand how algorithmic difficulty translates to human experiences. Looking first at A-star, as the number of puzzles region increase from 0 to 3, the number of moves increases gradually and solve time rises slightly, but it remains extremely fast under a few seconds even in the hardest case. This confirms that our maps are computationally solvable and structurally valid. Now we compare that to human performance. Humans take significantly more moves and more time. For example, with 3 puzzle region, A-star solves the map in about 2.5 seconds using roughly 125 moves, while humans take over 75 seconds and around 176 moves on average. This gap is important. It shows that while the map are technically solvable, they remain meaningfully challenging for human players. Here we compare the different approaches using both user questionnaires and gameplay metrics. First, looking at the ranking table, lower is better. ORP consistently ranks best in fun, novelty, visual quality, and overall preference. That tells us players enjoyed optional puzzles the most. RRP, on the other hand, ranks highest in difficulty, which makes sense because puzzles are mandatory. It increases challenge, but that doesn't always translate to higher preference. Interestingly, the baseline WFC generation without structure performs worst across almost all categories. This reinforces our earlier point. Visually plausible maps are not necessarily enjoyable or playable. Now looking at the player-facing metrics, ORP achieves a 100% completion rate while vanilla WFC drops to 14%. That's a massive difference in solvability. RRP and ORP both increase completion time and total moves compared to the input map, meaning that they successfully add complexity, but ORP strikes better balance, challenging but still fully completable. So I can show you a demo. So here is the basic Viridian map as we see in the game. There is nothing much to do except for just going through the maze itself. So this is one of our method. So the this is the optional rock puzzle. So if the tester wants to complete, okay. So if the player wants to actually use that to solve the puzzle, then they can, or else they can just skip it. This is the required rock puzzle method. Here the player has to solve the puzzles to unlock the end or get a candy. So he got the rare candy, and now he can go ahead. Yes. So thank you.
And today I'll be presenting my bachelor's thesis project on the effects of randomized resources on trading card games, specifically through studying Genius Invocation TCG, which is a trading card game. So just for background, this is a kind of like moderate complexity trading card game. Like, it's definitely less complex than the more classical study games like Magic the Card Gathering, if you guys have played that, or like maybe Yu-Gi-Oh, right? But it's like relatively new. When I did this study, it was released 2022 as part of version 3.3 of the open world exploration game Genshin Impact, if you guys have played that. And to date, there are over 100+ character cards. So the characters are like the cards where you can see these people, right? And then there's a lot of these accompanying supporting action cards. So there's over 350 of those in the full-size game. And the focus of my presentation is kind of on the randomization that is introduced through dice. So in order to play any cards, there's always a dice cost. And specifically for Genshin, they use 8 different 8-sided dice. And so there's 7 elements in the game. So each character has a specific element that they correspond to, and thus every action that a character takes, it needs to expend a certain number of like a specific type of dice. And then the last side of this 8-sided dice is a side that can basically stand in for any element. This is called the omni side. In this project, I wanted to simplify a lot like the effects of this randomization, so I focused on just one character, and then that character specifically is the cryo dice, so that may be referred to later in the presentation. But yeah, as you can see, like with so many dice, there's definitely like a lot of different combinations. I would say there's probably there's around 6,400 like unique combinations that you can make with this 8-sided dice, and that definitely has a big impact as you have to roll like every single round, and there's like 15 rounds in the full game. Cool. And then for the related work, originally I was trying to use this full-size simulator. Someone's been working on it for years and years before. But it's still in progress. Even like now, only about half of the cards and half of the characters have been implemented. They do have a lot of the mechanics, but I think they lack kind of support for like modifying the number of dice that we use, or like kind of like controlling like different parts of the aspect, since their goal from the beginning was just to create a full simulator of the full game. So yeah, I just found that there was not a lot of support for like Stable Baselines 3 or any other libraries or wrappers, so it's difficult to add ready-made reinforcement learning agents. So my goal was to create like a very simple like simulation environment that would allow us to isolate the effects that we wanted, while also like allowing very easy implementation of reinforcement learning agents. So onto the methods, onto the environment design. So this is the gameplay loop. We simplified it from the full game. So in the full game, the setup phase, every single round, you would need to select cards. You would need to then, out of your deck of 30 cards, you would need to select 5 cards, and then you would need to roll your dice. And then you would have the actions, and then after every round, it would go back to the setup phase. So I simplified it a lot. There's only 5 cards that you have in your starting hand. So in the simplified environment, you start with all 5 of them. There's no deck for you to draw cards from, but you still have the dice rolling. That happens in the setup phase. So also the characters involved. So there's one character, Kaya, and he has 3 attacks. So that's 3 possible actions. Each of these has a different cost and a different like damage effect. There are 5 supporting cards in the deck. So there's 2 food cards. There's 3 food cards, because one of them there's going to be 2 copies in the deck. They increase the health points. Then there's a weapon that will increase attack, and then there's an artifact that will decrease the dice cost. So there's one representative at least for every major category in the game. Yeah, so also, here's a summary of the simplifications made from the full game to the mini game. So in the full game, you always have 3 characters, and so these characters can have different elements. So there's also a lot of different like elemental reactions too involved in their attacks. But so here we only have 1 character, so we've simplified that aspect. Then I've made it so that there's only 4 dice per turn because the simpler game doesn't require as many dice. And then we've made it so that you can only play 1 action. So an action would be like doing an attack or playing a card. So you can only do 1 per turn, and then it goes to your opponent. And then, like I said, there's only 5 cards in the deck. So in the mini environment, here's kind of an overview of the cards I introduced. So food, artifacts, and weapons. And then there's 2 main environments that we are comparing between. So the deterministic one, which has really no randomness, and then we have the random environment. So as you can see, they both have the same number of dice, but for the deterministic one, these are all the omni dice. So as you recall, you can use these wherever. They can substitute for any element. And then for the random one, you have 4 random dice, and there's an automatic mulligan, which is like you can re-roll the dice that are not the element you want. This is also present in the full game. Yeah, and then the 3 main attacks that are element specific, we've changed kind of the number of dice. Specifically, you can see on the random side, it does start to require specifically cryo dice. And actually, this for balance-wise, I think it made sense here too, because the burst, which is the most powerful attack, as you can see, does 4 damage. It only requires 2 cryo dice, and given the automatic reroll, we can expect about 1.5 cryo or omni dice, or like usable dice. So it should not be super hard to use the burst. Yeah. So then onto the experiments part. So setting up this reinforcement learning environment, I was using the petting zoo environment. So that's basically this nice framework for creating multi-agent reinforcement learning environments. It's the multi-agent version of Gymnasium, if you guys have used that. And to set up an environment here, you need to define your observation space and your action space. So it's actually not super big. You can see the actions are the ones that we've outlined, and there's an additional end round action. This is not a skip turn, but it will end your round. So after you do this, there's no cost. You can do it any time, but you cannot play any more actions within this round. And yeah, so we're training the agents through self-play in this environment. And then for any reinforcement learning environment, you also have to set up rewards. So here are the typical win-loss rewards. I gave very high win-loss rewards and then a very small tie penalty, since I thought maybe ties would likely happen given the dice constraints. And then I provided further shaped rewards because the agents you have to give some direction, right, for the agents to learn how to win a full game. So here are some like common strategies or common mistakes that were turned into shaped rewards. So one of them obviously is playing an invalid action. If you don't have the dice required, then you cannot do it, and that comes with a penalty that originally was pretty high because I wanted agents to learn how to not incur this penalty, but it turned out that it made the agents actually too scared to actually play any actions during the training, because they were playing against themselves in the self-play training, and so then they would just always pick end run action to avoid this penalty, and then it actually lost like 100% of the time against the random agent, because the random agent would at least occasionally like play some attacks. There's another action I found that the agents were doing that was just ending the round with no dice available, or sorry, with all of their dice available. So they made no moves. That was bad. And then also if they use a food item with full health, that is obviously like a common sense. It's a waste of their resources. It's a waste of the dice used to play this food card, and it's also then they can't heal later. There are also some rewards given for good actions, like attacking. So attacking comes with a small reward, and then it also comes with an additional reward depending on the damage that they have done to the opponent. So in this case, the damage is ranging from 1 to 5. And then using a support card will also give them a small reward. The agents involved, I've only used the PPO agent, so the Proximal Policy Optimization agent, because within the Stable Baselines 3 library that I wanted to integrate with, only this reinforcement learning algorithm came with like an official masked variant to allow us to use an action mask during the training. And then there's also a random agent as a baseline. And of course, also the masked agent does not have an action mask in the testing. And then finally, for my results, I first ran a balance check in both environments just to tell if there was like a significant first player advantage. I found that there was none, but obviously the randomized environment, it did cause a lot of ties because of the dice constraint once it reached 15 rounds. And then here's the main results. So for the deterministic environment, PPO won overwhelmingly, and actually the masked PPO agent actually performed worse than the unmasked agent. I think this was because the reward landscape probably for the masked player was a lot more like flat because it never really got penalties from invalid actions. So it never really had a chance to like it could only try out the legal moves. I think at least that's my hypothesis. And then for the randomized environment, we kind of see the same trend, except there's a lot more ties. Yeah, so here is an additional summary of the other changes I made to get to the shape rewards I did, or why I added rewards for using cards or for not using cards. Yeah, so I guess notably it was just that there was a small hiccup in the middle where we had added this HP bonus, and it was actually like doing more bad than good. And then for the food usage, it was also having this unintentional encouragement effect of encouraging the agent to use their cards even when it was unnecessary. Yeah, so then onto the overall results summary. There's 2,000 games run per environment, so 1,000 where PPO was first player, and then 1,000 where the random agent was the first player. Yes. Okay, so yeah. So in total, the project had 2 custom petting zoo environments. You can insert any like stable baselines theory, like implemented reinforcement learning algorithm in here, and these 2 are both balanced because there's no first player advantage, and there's a clear distinction between the deterministic and randomized environment results. And the code is available online, and I think next steps would be like probably to create more incrementally complex environments to study like how the agents can respond to increasing complexity. I don't think this would necessarily mean more ties because more mechanics allow you to do things like tuning your dice so that you can get more dice by sacrificing cards, for example. But there's a lot of additional mechanics that were not implemented here. But yeah. Okay, thank you.
My work is on an LLM agent for playing and explaining chess moves. So briefly, the motivation, obviously, strong game AI in games like chess or Go are very, very good. They can be human players, but they can't explain themselves. They don't have generally don't have a rationale for why they make a move. On the converse, language models can explain well. They can generate natural language at a high level, but they are not good at these games because they have no method of calculating. So the idea is, can we fine-tune an LLM to combine the competence of an engine at some level and the clarity of an LLM into one system? And this would be good for primarily for a coaching aspect. So players that are learning to play, if they make a bad move, or if the AI makes an adversarial move against them, they can explain why that was a good move or why the move punishes a mistake that the player made. Also, spectator value. In a game between 2 grandmasters, if a lower level player wants to watch and enjoy the game, they may not understand why a particular move is good. So potentially an LLM could explain the rationale behind a move in a game. So chess is sort of a classic example of a game AI sandbox. I have a picture there of Garry Kasparov playing Deep Blue in 1997. That was kind of the breakthrough moment where AI could defeat human masters in a game in 1997. Now, Deep Blue is a supercomputer. It ran on about 500 CPU cores. Now you can have Stockfish on your cell phone, and it would beat the best players in the world 100 out of 100, no trouble. So we've come a long way, even in the last 30 years since Deep Blue. But also AlphaZero, about 10 years ago now, from Google DeepMind, purely learned based on reinforcement learning self-play. and use Monte Carlo tree search based off of what it learned in terms of its policy network from playing itself billions of times. So the core idea here is, can we use a chess engine to determine the best moves? Can we use facts algorithmically about the board to generate algorithmic human-style explanations, and then combine those two into one, fine-tune a language model to imitate the engine and the algorithmic explanation generation into a single compact language model. And so, yeah, can a small model generate reasonable moves and rationales? We're using a 4 billion parameter model in this work that's fine-tunable and runnable on consumer-grade hardware. That was kind of my goal here. So this isn't entirely a novel concept. There was a work from last year which created a system for, given two moves fed into an LLM with a position, it would explain which move is better and why. And that's on an 8 billion parameter model. Also ChessGPT from a few years ago, which explained moves that were made. It didn't make moves itself, but it explained moves that were made based on a large corpus of text. So books and videos, expert annotated games, etc. So our pipeline is a bit different. We just look at games which are played. So from Lichess, we grab games which were played by players online. So some subset of players that are just, average 1,000 ELO level players. Some subset of elite players, so into the master realm of 2,300 ELO. And we sample positions from those games. So given a game, randomly select after move 11, here's what the board looks like, and it's white's turn to move. And then do that for a lot of games. We label the best moves in those given positions using Stockfish, which is among the stronger engines today. We label the best move and we label the next few best moves. Then we generate a strategy and a tactic, one sentence for strategy and one sentence for tactic. And we do that automatically, and I can explain a little bit more about that in a second. But given the combination of the best move and the fine-tuned strategy and tactic sentence, we can fine-tune a small model on those. So we just give, for prompt, we give the board state and basic instructions like you're a chess assistant, give the best move in this JSON output structure. And we anticipate a structured decision with rationale. I talked about algorithmically generating strategy and tactic sentences. Strategically, these are things which are long-term advantages for the player whose turn it is. So if you make a move which improves your central control, that doesn't do anything inherently, but in the long term, that could benefit you. And these are things which we can determine if we just look at the board state. If we have certain algorithmic flags set, we can say, does the player playing white have control of the central four squares of the chessboard? And if so, we can give it a little bit of a boost. Hey, this move improves central control. We control more of the central squares than we did before. Tactical signals are more one move type things. So if you take your opponent's queen, that's generally a good thing. If you have mate in 2, that's generally a good thing. These are things which we can label as well. As for training, we use Qwen3, 4 billion parameter, the instruct version, so no thinking capability. It has thinking capability, but no explicit thinking steps. It's the 4-bit quantized version of the model just to improve the runtime and the fine-tuning time on my hardware. Fine-tune with LoRa adapter. There's a built-in LoRa via MLX for Mac, which I used most recently, but I've used QLoRa via bits and bytes when I was running on Windows on a CUDA CPU, or CUDA GPU, sorry. Like I said, it runs on consumer hardware. So I use a 6 gigabyte GPU, about 24 to 30 hours of fine-tuning time for the model on Windows, and then a similar training time on MacBook Air with the other setup. Results does quite well. We have a 36% top 3 move agreement with Stockfish. That's not great, but more happy with the fact that we have 100% compliance with the JSON structure, which I requested, and it 100% of the time plays a legal move. I do attach a list of legal moves and say pick from one of these, but sometimes LLMs struggle to pick from a list of things which you give it. So I'm happy with the fact that it does that. So it does do well in check situations, but obviously your move set is limited when you're in check, so I expect it to do a bit better there. I had this idea. This needs to be further fleshed out in future work, but rather than just prompting the LLM for a move, what if we had a Monte Carlo tree search style agent like AlphaZero at the root, prompt the LLM to give its 5 or 6 best moves, branch into each of those moves, simulate a certain depth, and then at the depth which you're satisfied, have the LLM tell you which side is better. This needs fleshed out more, but I think it's an interesting idea that I can explore in future work. I did create a little bit of a GUI. You can play against either the MCTS version, which is still a work in progress, or the traditional LLM direct, here's your move, here's why. And yeah, it adheres to the rules of chess. I have a brief demo here. So you can see this is the Monte Carlo tree search player. So oftentimes I've noticed the Monte Carlo tree search player doesn't return a strategy or tactic sentence at the top. It just doesn't come up with anything. It also takes a very long time to play moves. You notice it takes 110 seconds to play Rook G8, which is a terrible move in this position. But overall, pretty interesting. And then I switch it back to the LLM mode here. At some point. So yeah, now I switch it to LLM mode. I respond. This is a bit quicker. It'll play responding move. So yeah, that only took 7 seconds, which is not too bad, given we're just running on a MacBook. I ran this on my computer, and it gives a reasonable strategy. I would say that does increase center control. That knight sees d4 and e5, which are both central squares, and it does have more pieces active than me. It has 2 knights rather than 1. You'll notice that, given that though, it still is not very good. So I'll attack its knight. Best move is probably to not do what it does, but yeah, that's bad. That hangs a knight in one. So anyway, I'm happy with what I have here, but it does need work. So small models can operate inside a structured rule system. So given a legal move list, it does return valid JSON, which indicates one of the legal moves which I gave it. And I think that the explainability portion can help with player learning, assuming that we can prove that it matches up with the moves that it's making. It does lack some ability to play strong logical moves in an adversarial role. It will never beat Stockfish, at least not with this setup. It'll never be at a master level with this setup. But with some different ideas, we could potentially get to the point where it's a useful player for practice. Future work for me, I think, is more self-play games. We need more data. I'm fine-tuning an MCTS version of the LLM, so instead of generating a move, a tactic, and a strategy, it generates a move evaluation. So like, how good is this position for you? And then a tactic and a strategy sentence. Given that valuation, we can use that at the depth at our leaf nodes in Monte Carlo tree search to inform which path up is best. And then different models or adapters to handle move, valuation, and strategy. I think this could be useful rather than having one model do all 4 things. Delegating tasks to specific models could improve performance in the long term. These are the papers I discussed earlier. Thank you.
The question is that can I solve the Fibble variant of Wordle? It depends on how many lies I introduce. I think with one lie, I played it last year, 10 games. I think I solved it 70% of the time. So, yeah, I didn't even attempt that.
Fibble is much harder. I tried. I'm pretty bad with Wordle to begin with, so I couldn't do it. And in one of my classes, I asked students to actually solve it. And there was one guy come out and say, I get everybody in my dorm to do it together, and one word couldn't do it. But there was once I played in class with everybody in the class, like 20 plus students do it together. We were able to solve it. Fibble 1, that's Fibble 1. I know Lisa solved the Fibble 1 before, right? You solved Fibble 1. But the Fibble 2 is really hard. Fibble 2, you have to pull out paper and do these reasonings.
So you should try to, write a paper on this as an AI benchmark and also release it as an AI benchmark, like basically build the harness and everything for it. And then, because people, benchmarks that are easy to use don't cost a lot of talking about scale a lot. They are much wanted.
Thank you. We are thinking along that way. So in addition to the Wordle Arena that the team showed, we also have a Fibble Arena, Fibble 2 Arena on the same site. And then we run once a day to solve the word of day. So over time, we'll see how these large languages do. So the latest result, Google just came out Gemini 3.1. It solved Wordle, it solved Fibble, it solved Fibble 2, okay? But it failed the Fibble 3 for now. So we'll see how it does going forward.
Owen, I'm curious as to how much variability you found in the chess model. Was it generally doing the same things? Was there a great deal of variation?
Yeah, so the question was how much variability was there in the model's chess moves. I found a little bit of variation. I think that it really likes to move knights in the opening. And then I do find it makes sometimes a logical defensive move when it's under pressure. Really likes to move knights, though, I think. I think it likes the idea of going as far forward as it can with pieces on the back rank. So I would say that's the general strategy I picked up on, but it is pretty variable in terms of its actions.
So, I may not have fully understood, so excuse me if this question was explained in the presentation. I really am trying to understand. How, if you're using a reward function with RL with petting zoo, do you help whatever you're training attribute success or failure not to the interfering dice roll randomizer? So you could make a good early move and be punished because dice roll just randomly made it so that was not great for you. So you could make the right move as the RL agent, but still have failure state because of the dice. Because the dice are kind of interfering and intersecting with good moves. So it's like, how do you solve for the RNG factor when that's out of the hands, even if the RL agent is making better and better moves, because there's this interference happening with the RNG. And I don't know if this was what you were trying to explain with the 6400 like permutation outcomes for the dice, but I still don't understand how we get a model to properly be rewarded if it's doing the right thing and still having a bad negative outcome. And maybe you could explain a little bit more of your shaping strategy around that, because I didn't fully grasp.
Good luck repeating that question.
Right.
It's like, how did the dice make it complicated?
Right. I think honestly, I feel like these are kind of like separate in the sense that the actions that you're allowed to take are determined by the dice, but we're kind of like, I don't think I never penalize an agent for, like, there's no objectively good or bad action, right? Like, you have an action space and these 8 actions are all theoretically available, but we're only judging these bad actions in terms of like things that are not related to the dice, right? So like for the food example, right? The dice don't actually affect like whether or not this food action is available. If it's available and you're able to take it, that's plus points, right? But you aren't going to be penalized for not being able to take it because you don't have the dice to eat this food, right? So I guess my answer is also a bit confusing. I'm sorry. But yeah, I feel like the function of the dice was just to kind of change like the actions you had available. But then these like objectively, what I said, like were common sense strategies, right? These are kind of built on top of like your existing action set. So none of these are saying, well, there was this action you could have theoretically taken if you had the dice for it. And then therefore I'm going to give you a penalty for not doing it. It was more just like if you had this action available to you, you could have gotten this higher number of points, but if you couldn't have taken it, then there's no explicit punishment for that.
Okay, so for follow-up, in a slightly more simplified example, if we took any like German style or Euro board game where you could draw dead with the dice, you could have really good strategy in like Catan, right? Really good strategy, do everything right, but draw dead because the way the dice rolls happen just are very unlucky against the expected distribution of dice. So you could have the RL agent doing its job right, but get negative outcomes. So with sparse rewards, you would essentially you discourage that model from following a successful strat. That's my concern. But I don't think I understand enough about how this works to say how we're solving for it. The TCG example you give is complicated by the fact that it has this extremely arcane way of the action space being defined by the dice, much more so than a simplified, like, you get these numbers on the board activate or whatever. So maybe I don't understand the game fully or how this approach works, but that was my question, as uninformed as it is.
I see. I think I understand your question now. So your question is not really like for a single run, like maybe there's like a reward that would like influence the agent. Your question is like if the agent had this good strategy and they were testing it out, there could be just some run where the dice rolls are so bad that they are, in comparison to other runs, the reward is going to be lower, right?
Yes.
Oh, okay.
This is also like if someone's playing poker, they've got like the amazing hand and their opponent happens to have an even rarer amazing hand, right?
Right. I guess the kind of hope is that since all these dice rolls are kind of uniform, it's like in expectation, right? You would hope that these extremely rare, extremely bad scenarios, like an agent isn't just going to try this run once, right? Like they're going to just try their strategy once, and if it's really bad, then they just give up on it, right? So you hope that like, even though like it'll try like a few times, right, before it says, okay, I think this is a really bad strategy. So in those few times, it's just so unlikely that the dice are just so bad, like every single time, that it would actually make the agent think, oh, this strategy is something that's bad, not just that I got unlucky. I think.
What would you have to run before those dice even out? So he's right. I mean, plenty of times I play Catan, and I'm like, I play Catan with eights and sixes, right? And then I'm like, 12 again? What the hell? So, but you know, with the dice, I mean, the whole concept is eventually, with enough samples, right, the roll of the dice will even out, and so then the individual tactics will start to rise up. How many do you think you would have to run before you could count the dice as being normalized?
Right. So I think in my presentation, I did say that especially for the randomized environment, you would expect 1.5 usable dice per round, right? There's 15 rounds. I guess if you count this like 1.5. Sorry, I'm not gonna on the spot probability calculations, but I don't think it should be too much, right? So,
6 to the 15th plus, 6 to the 15th plus 6 to the 15th plus 6 to the 15th.
I guess I'm specifically thinking about what the probability is of getting 1.5 or more usable dice in that round.
Alright, then it would be 2 to the 16th.
There's 4 dice.
There's 4 dice. 4 to the 16th plus 4 times. Alright, 1 to the 16th plus 2 to the 16th.
That's a huge number.
A very
That's a
low.
huge number. Yeah. So this.
Very expensive number.
That's why this is a very hard problem to train with reinforcement learning. It needs a lot of GPUs really, you know.
Probability.
Yeah.
Okay, last question.
I got a question too.
Yeah, you're keen. Let's do that.
This is for the dungeon creator.
Oh, hi.
Okay, so in my former life, like Conway's Game of Life was a giant predictor of like how to create dungeons and things. I don't know if you're familiar with the Conway's Game of Life algorithm.
No.
It's from the 70s. It's really cool.
Okay.
So, and so cellular automata. So I was going to ask, like, did you try cellular automata to generate? Because that's kind of how it was done and still is done in like certain SimCity games. When you're generating landscapes and features like that, where it actually like grows the roads and it grows the power lines, like when you're trying to just generate a map, right? And it's all based on the seed that you started with. And sometimes you get really cool results, sometimes you get like really bad results. But I was curious, like, did you try that? Was that like part of your generating these dungeons? Or did that inform any of the choices you made?
So the question was that have we tried the cellular automaton algorithm for my project? So we didn't use that first because I didn't know about that till now. But we tried using basic algorithms to get something done in the Pokemon Fire Red space. But the problem we were trying to solve was to inject the Sokoban puzzles in a maze type scenario. So that was our actual goal than just creating a visually plausible good map.
Could you explain the difference between the wave function collapse
Yeah.
and how it works?
Yeah, so the wave function collapse is a constraint satisfaction method. So let's say we have a tile set of, let's say, 5 tiles. So one is grass, one is wall, one is rock, and etc. So if we have a solution path, so the solution path can never be a wall tile. So the the probability of the solution path tiles would be just the grass path or the maze path. So based on that, the adjacent tile adjacent tiles probability would be, it can either be a grass path or a wall path, but it cannot be a rock path. Let's say, so rock tile. So the probability decreases and the entropy decreases, and it then eventually collapse into something which is actually based on the constraints that we have given to the algorithm.
Okay, this really sounds a lot like what I described. So
We're at lunchtime. You want to, Julian, I want to ask you, keynote privilege.
I know. I'm not gonna hold like a long talk about this, but I do. Basic problem.
Take the mic to the stream.
The basic problem is that both wave function collapse and cellular automata are at the core local algorithms that look only at the next tile. And the problem that a lot of these, like Pranav's work here, a problem that a lot of these approaches try to solve is how do you reconcile that local algorithms based on adjacency constraints are good at capturing visual style and various other kinds of style, but it cannot capture global things such as playability. Is this thing reachable from this? So there's been a bunch of different ways of trying to solve this and combine this in different ways. So this is where Pranav is presenting is one way of doing this.